Imagine trying to upgrade a massive AI model's memory,
Right.
but you're not doing it by just throwing another $1 billion worth of silicon at it.
Yeah, no more buying massive clusters of NVIDIA chips just to brute force the problem.
Exactly. I mean, if you follow AI hardware even a little bit, the physical limits we are hitting right now, with power consumption, silicon yields, all of that. So today we are doing a custom-tailored deep dive into an engineering effort that tries to sidestep that physical wall entirely.
And they're doing it by fundamentally changing the underlying laws of mathematics that the model uses to actually think.
Right. We are looking at the Shannon Prime inference engine. Specifically, we're digging into a massive architectural shift that they call the Friedman stack.
And I have to say, the documentation we are reviewing for this today is incredibly dense.
Oh, yeah. It's intense.
I mean, we are looking at their internal engineering specifications, the mathematical proofs justifying the whole architecture, and, the raw system benchmarks. The overarching goal of our deep dive today is to evaluate the exact criteria required to ship this Friedman stack as a default production-ready engine feature.
Which is a huge deal, because what they're attempting to do here is essentially replace the standard continuous floating point mathematics of AI memory with discrete topological trees.
Right, which sounds abstract, but it's a shift that promises massive compression, perfect mathematical stability, and perhaps most importantly, zero drift.
Zero drift is literally the holy grail. I mean, if you have ever tried to run a local language model on your own machine, and you've noticed it slowly losing the plot during a really long conversation, like it gets confused or starts hallucinating.
Yeah, it just forgets what you were talking about 20 minutes ago.
Exactly. And a huge part of that is mathematical drift. So to really understand the shipping criteria for the Friedman stack, we have to look at the bedrock mathematical environment they're building from the ground up. Standard AI math relies entirely on floating point arithmetic.
Yes.
It's continuous, sure, but more importantly, it is fundamentally blurry.
Blurry is a really good word for it. It is inherently blurry because floating point arithmetic on a standard GPU is just not truly associative.
Right, the order of operations messes it up.
Exactly. I mean, in pure math, if you add A plus B and then you add C, you get the exact same result as adding B plus C and then adding A. That's just basic algebra.
Right.
But when you are dealing with 16-bit or 32-bit floats, the computer has to round off these microscopic decimals at every single step just to fit the numbers into physical memory. So A plus B plus C might actually give you a slightly different value at, the millionth decimal place than A plus B plus C.
And in isolation, who cares about the millionth decimal place?
Yeah, right, exactly. But in a transformer model with billions of parameters, doing trillions of operations across 96 different layers, those microscopic rounding errors cascade.
They accumulate.
Yes, they accumulate, and that is what drift is. The actual mathematical foundation of the model's thought process physically degrades over time.
It's like you're building a skyscraper, but every time you add a floor, your ruler shrinks by a fraction of a millimeter. By the time you get to floor 90, the windows don't fit into the frames anymore.
That is a perfect analogy, and the Shannon Prime team's answer to this isn't to just buy a more precise ruler like moving to 64-bit floats.
Right.
Their answer is to stop using rulers altogether and switch to interlocking bricks. They are moving the transformer's entire hidden state into a framework based on a complex multiplication elliptic curve.
Okay, now we're getting into the heavy math.
Yeah, specifically, they're operating over an imaginary quadratic field. And the core engine of this entire thing is a very specific number. It's the Heegner number, -163.
-163. Why that specific number? I mean, what makes -163 the magic key here?
So, operating over the field denoted as q adjoin the square root of -163 is what guarantees absolute algebraic stability for the system.
Okay.
The reason this specific Heegner number is the absolute linchpin of the whole architecture is that it possesses what mathematicians call a class number of 1.
A class number of 1.
Right. And that dictates that its ring of integers forms a unique factorization domain, or a UFD.
Okay, let's ground that a bit for the listener. So we enforce a unique factorization domain to basically guarantee that every matrix multiplication in the neural network collapses into one and only one canonical state.
Exactly one, yes.
Because with standard integers, the number 12 only factors into prime numbers one way. It's 2 times 2 times 3. There's literally no alternate universe where 12 factors into something else.
Right, that's just basic arithmetic.
But when you move into complex number fields, you often lose that property.
Right.
Right? A mathematical state might actually factor in multiple different ways depending on how you approach it. And the moment that happens in an AI.
You lose determinism
Hmm.
completely. You introduce ambiguity into the core logic gates of the intelligence.
Which is terrifying if you want a stable system.
Exactly. So by using Hegner -163 and securing a UFD, every single linear algebraic step of the AI's inference process can be expressed exactly in integers.
Everything, the projections, the attention mechanisms.
Yes, all of it. Layer normalizations, everything. There are 0 decimals to round off. There is absolutely no microscopic variance. Exact mathematical inverses exist for every single map in this space.
Wow. So if you transform a vector forward, you can mathematically transform it backward and arrive at the exact bit you started with.
The exact bit, yes. The operations are perfectly lossless on their own algebra.
So going back to our analogies, instead of a smooth, continuous volume slider, where you can never quite hit the exact same decibel level twice because your thumb shakes slightly. Right. The system now operates on a heavy mechanical dial. You know exactly what notch you are in, and there is physically no space between the notches. The mathematical state moves from point to point on this elliptic curve without ever accumulating a single fraction of drift.
Which is an incredible foundation. But since we have established this perfectly discrete notched dial, we immediately have to address the physical limits of the dial itself.
Right, how many notches are there?
Exactly. The Shannon prime framework uses complex multiplication theory, or CM theory, to define strict, mathematically provable information capacity limits for every single layer of the AI.
And they govern this limit using something called the Haswell bound.
Yes, the Haswell bound.
This is where it intersects directly with standard Shannon limits of information theory, which I find fascinating. The documentation gives the explicit formula for this bound. It is n of p is less than or equal to p plus 1 plus 2 times the square root of p. And this formula determines the absolute maximum number of distinct hidden states that are mathematically reachable at any single layer of the transformer.
So let's unpack the mechanics of that formula real quick. The p in there represents the specific prime number they are using for their arithmetic modulo.
Right, it's their mathematical sandbox for that specific channel.
Exactly. So the Haswell bound dictates the geometry of the elliptic curve over that finite field. The p plus 1 gives you the baseline number of points on the curve, and that 2 times the square root of p acts as the theoretical variance, or the maximum allowable deviation.
Okay, so when you map this to AI architecture, what does it actually do?
It acts as a fundamental hard-capped limit for the transformer's capacity to hold information. It is the Shannon limit of the channel.
Okay, so the documentation actually runs an example to show this in practice using the prime p equals 41.
Yes.
If you plug 41 into the Haswell formula, the maximum capacity per coordinate per layer works out to exactly 5.78 bits.
Right, around 5.78.
But hang on, 5.78 bits is tiny. I mean, if you follow standard open source models right now, you know they typically run on 16-bit floats. And we are really just now seeing 8-bit quantization become standard for running things locally.
Very true.
So if we hard cap the model's capacity, roughly 5.8 bits per coordinate, aren't we just severely bottlenecking the AI? I mean, it feels like we're stripping away the model's ability to hold on to nuance.
Well, it only looks like a bottleneck if you assume all 16 bits of a standard float actually contain useful information.
Oh, and they don't.
They absolutely don't. The restriction to 5.78 bits doesn't bottleneck the AI. It forcefully filters statistical noise.
Interesting.
See, standard models using 16-bit floats are overwhelmingly just memorizing garbage variants in those lower decimal places.
Yeah.
They're literally trying to assign semantic meaning to the equivalent of microphone static.
Okay, so the 16-bit float is like a microphone that's way too sensitive. It's picking up the hum of an air conditioner 3 rooms away, and the AI is wasting massive amounts of compute trying to figure out what the hum actually means in the context of the prompt.
Exactly. The Haswell bound acts as a harsh mathematical noise gate. It only lets the actual semantic signal through. It forces the network to only encode what is mathematically novel.
Wow.
The theory literally proves that if the trajectory of the inference process visits the maximum distinct states at layer L, it mathematically cannot extract any additional information at layer L plus 1.
Because it's already full.
Right. The model's expressive capacity is rigidly physically bounded by the theorem. And this is what perfectly validates the entire framework against classical Shannon channel limits. It mathematically defines the maximum rate of error-free transmission through the transformer.
And because we know the absolute maximum limit of the signal now, we can compress the model safely without destroying it.
Which brings us perfectly to quantization.
Right. Because if you are a developer trying to squeeze a massive 70 billion parameter model onto a consumer graphics card, you have to quantize it. You have to lower the
I'll
precision.
have to make the model smaller.
Exactly.
Yeah.
And usually you use a standard method like AWQ or GPTQ, but that process is inherently destructive. You basically take a mathematical chainsaw to the weights to make them smaller, and doing so destroys the really delicate multiplicative relationships that the model learned during its training phase.
Yes, you are actively breaking the model to shrink it.
Right. And to fix it, you have to run a calibration pass. You pump 1,000 samples of text through the broken model. You see where it hallucinates or spits out garbage. You calculate a Hessian matrix of all the errors, and then you try to glue the parameters back together so it somewhat functions again.
Calibration is basically a giant Band-Aid for unpredictable rounding errors.
Yeah.
But in the Shannon prime engine, because of the math we just talked about, they use a methodology called Sato-Tate mixed precision. And this methodology completely eliminates the need for any calibration data whatsoever, zero calibration.
Shrinking the model perfectly without needing a single test pass to see if you broke the intelligence. I mean, how does the math actually allow for that?
Well, because the model operates entirely on that complex multiplication curve we established earlier, lowering precision is not achieved by just rounding off numbers.
Okay.
It is accomplished by iterating a structural mathematical transformation called the Frobenius endomorphism.
That's a mouthful.
It is. An endomorphism is essentially a mapping of a mathematical structure onto itself that strictly preserves its algebraic properties.
Okay, so it shrinks it without changing the shape.
Exactly. And the absolutely critical mechanic here is that the Frobenius endomorphism commutes with the layer operations of the neural network.
Okay, let's clarify. Commutes,
Hmm?
meaning the order of operations doesn't change the final outcome.
Yes. You can apply the transformer's heavy layer multiplications and then apply the Frobenius reduction. Or you can apply the Frobenius reduction to shrink the precision first and then run the layer multiplications.
And the result is identical.
Mathematically identical. Lowering the precision via this method preserves the algebraic relations flawlessly. There is literally nothing broken to calibrate.
That is wild. And to execute this practically, the documentation says the Sato-Tate mixed precision leverages the specific behavior of prime numbers within this Heegner field.
Right.
Because primes here exhibit two very distinct behaviors. They either split or they are inert.
And this is where the mixed precision architecture gets its name. So inert primes, for example, the prime p sub 1 equals 2. They provide absolute zero drift quantization.
Zero drift at all?
None. The underlying math dictates that their Frobenius traces are strictly zero. There's zero variance.
Okay.
But split primes, like the p sub 2 equals 41 that we discussed earlier, they do have variance, but they possess a bounded analytic drift.
Bounded because of the Hasse-Weil limits.
Exactly.
So it's essentially a hybrid engine. You pair a 2-bit channel using the inert prime, which is like your electric motor, perfectly clean, zero variance, zero emissions, with an 8-bit channel using the split prime.
Yes.
And the split prime is your gas engine. It generates some exhaust, some variance. But because of the Hasse-Weil bounds, we know the exact mathematical maximum of that exhaust before we even turn the engine on. We don't need to test drive it 1,000 times to see how it will perform.
Exactly. By mathematically combining that 2-bit inert channel and the 8-bit split channel, the engine creates a 10-bit mixed precision format. They call it FP10.
Right.
And this FP10 format is entirely variance-free regarding unpredictable drift. It requires absolutely zero calibration data to deploy. It just works.
Okay, so we have proven we can compress the math without drift. We have our notch dial, we know exactly how many notches it has, and we know we can shrink it safely using Sato-Tate. But now, we hit a massive physical reality wall, because the engine has to translate messy, unpredictable human language. You know, the prompt you actually type into the chat box into this pristine, discrete mathematical environment, and it has to do it in real time.
Yes, that is the hard part.
How does it actually convert a typed prompt into an algebraic state? And that is the job of the very first tier of the Friedman stack, the KSTE, the Knight-Spinor Tree Encoder.
The KSTE is brilliant. It bridges the continuous world and the discrete world.
Okay, walk me through it.
So the standard input to an AI attention mechanism is a key vector. That is typically a continuous 128-dimensional array of decimal numbers representing the semantic weight of a single token.
Right, like the word apple becomes a list of 128 decimals.
Exactly. The KSTE takes that continuous 128-dimensional key vector and it structurally converts it into a discrete 60-node topological tree with 3 specific labels.
So it literally turns a list of numbers into a branching tree. Normally, an AI looks at a 128-dimensional vector, like a dense cloud of decimal points floating in space. But the KSTE strips away the cloud and just hands the system the solid constellation lines. It discards the exact numerical scalar values entirely.
Completely throws them out.
It only looks at the order pattern, the ranks of the absolute values, and whether they have a positive or negative sign.
And discarding those exact scalar values is the absolute key to maintaining the algebraic stability we achieved with the complex multiplication earlier.
Oh, because if you kept them.
If the KSTE preserved the raw floating point decimals, it would immediately reintroduce the non-associative drift we literally just spent all this math eliminating.
Right, you'd be right back to blurry math.
Exactly. By relying purely on the rank and the sign, the encoder guarantees bit-identical tree construction. The conversion process is entirely deterministic.
But wait, if we throw away the exact numbers and just keep the rank like this value is the biggest, this one is second biggest, don't we lose the specific magnitude or the loudness of a semantic feature?
What do you mean?
Well, say the vector dictates that the concept of urgency is at a level of 100 and politeness is at a 2, versus another token where urgency is at a 5 and politeness is at a 4. The rank is identical in both cases, right? Urgency is number 1.
Yes.
So don't we lose incredibly critical linguistic nuance by just saying urgency is first?
It's a great question, but the nuance is not lost. It is translated. The KSTE converts that scalar magnitude into structural depth within the topological tree.
Structural depth.
A residual value in the vector that has a massive numerical magnitude doesn't just get a higher number assigned to it, it translates into a long downward branching path in the physical tree structure. The loudness actually becomes a physical, topological feature of the memory.
Okay, let's walk through exactly what this memory layout looks like for a standard input.
Yeah.
Because the specs break it down.
Yeah, let's do it.
The encoder is remarkably lean. It reuses an existing 63-byte block format from the engine. It takes the 128 dimensions from the standard key vector and splits them up. It identifies the top 14 most important values based purely on their absolute magnitude. These 14 become what they call the anchors. The remaining 114 values in the vector become the residuals.
So the physical tree begins with an invisible root node. The 14 anchors are attached directly to that root node as children, and they're ordered strictly by rank, largest to smallest.
Okay.
These 14 anchors are all assigned label A.
And label A maps directly to that inner zero-drift prime lane we discussed in the Sato-Tate mixed precision. Right.
Precisely. It routes the most critical semantic anchors through the zero variance lane.
That makes perfect sense.
Then the encoder processes the 114 residuals. Each residual is attached as a child node to whichever anchor dominates it mathematically.
Oh, okay.
And this is where the signs come into play. If the residual has a positive sign, it gets label B. If it has a negative sign, it receives label C. And as you pointed out earlier, the depth of the resulting branch physically represents the original scalar magnitude.
There finally, the KSTE enforces a strict 60-node budget. If the resulting tree generates more than 60 nodes, it simply prunes the weakest, lowest magnitude leaves. So the entire complex linguistic concept of that token is packed into a tiny, completely predictable structure.
And because of that strict rank and sign methodology, it is entirely immune to rescaling.
Right.
The engineering specs mention a process called Frobenius shimming, which is essentially a scaling factor applied to the math to keep numbers manageable within the hardware limits.
Yeah, and in a standard AI model, scaling all the weights up by a massive factor of 10 might trigger huge floating point rounding errors.
Exactly. But with the KSTE, if you multiply the entire input vector by 10, the ranks of the values do not change at all. The number that was first is still first,
right,
and the positive and negative signs do not change. Therefore, the resulting topological tree remains completely bit identical. The determinism of the encoder supports order invariance flawlessly during that Frobenius shimming. Rescaling literally cannot break the memory topology.
Which is incredible. So the KSTE is churning out these perfectly stable 60-node trees for every single token you type into the prompt.
Yes.
But memory is finite, right? Even when it's highly compressed. If you feed the model a massive 100,000-word document, the system has to decide which of those trees to keep in the active cache and which to throw away. It needs a filter.
It absolutely needs a filter, and that filter is the Friedman sieve.
Right.
The sieve replaces the traditional method of variance-ranked memory eviction.
So standard AI attention mechanisms usually calculate a probabilistic score for how important a token is to the current context, and they drop the tokens with the lowest scores.
Right, which is just a fuzzy probabilistic guess. Sometimes it drops crucial context just because the math guessed wrong.
But the Friedman sieve doesn't guess.
No, it operates on absolute topological logic. It utilizes Friedman's well-quasi-ordering theorem.
Okay, break that down.
It fundamentally checks for homeomorphic embedding. When a new token is processed by the KSTE and turned into a query tree, let's call it T sub q,
To T sub q.
the sieve compares T sub q against all the existing key trees currently sitting in the cache, the T sub k trees. It scans them to see if the new tree, T sub q, structurally embeds into any existing T sub k.
Meaning, it's checking if the new constellation fits entirely inside an older, larger constellation.
Exactly. If T sub q embeds successfully into an existing T sub k, the sieve's logic mathematically concludes that the semantic information of the new token is entirely subsumed by the older token.
The new token brings absolutely zero novel mathematical structure to the cache.
Zero. Therefore, it is instantly evicted.
And this connects directly back to the house-wide capacity limits we talked about earlier.
Yes, it does.
The model has a mathematically hard-capped capacity for hidden states per layer. It literally does not have the physical room to store redundant data. The sieve has to ruthlessly drop any tree that doesn't introduce a completely novel mathematical shape, or the engine would just hit its Shannon limit and crash.
That is the functional necessity of the sieve, but the real engineering challenge is executing that topological comparison in real time.
Because comparing the branching structures of trees is traditionally very computationally expensive, right?
Extremely. And the Shannon Prime engine runs on edge devices, specifically targeting mobile hardware like the Snapdragon V69 DSP.
So to function on a mobile phone processor, the embedding check has to be almost instantaneous.
Right. The documentation actually evaluates the hexagon kernel complexity specifically for this constraint. The decision procedure for an ordered tree embedding runs at a complexity of big O of the absolute size of T sub q times the absolute size of T sub k.
Okay.
Because the KSTE strictly enforces that 60-node budget we mentioned, the trees are predictably small. A greedy embedding algorithm running on the hexagon DSP executes in a maximum of 3,600 steps.
3,600 steps, which is functionally instantaneous at the processor level.
Exactly. The embedding kernel fits easily within the hexagon DSP's vector tightly coupled memory, the VTCM, with plenty of overhead left.
But, and this is a big more, but achieving that speed requires a very deliberate architectural trade-off regarding the memory overhead of the cache slots themselves.
It does. It's a significant trade-off.
Let's break down that memory trade-off because I think it's brilliant but costly.
Yeah.
The raw data for a single token requires exactly 123 bytes. That's 63 bytes for the existing block data and 60 bytes for the packed KSTE tree representation.
Right.
But if the hexagon chip had to manually trace the ancestral relationships of the tree, like figuring out which node is the parent of which leaf, over and over during every single embedding check.
Those 3,600 steps would multiply rapidly. It would bog down the processor.
Exactly. So to bypass that latency, the engine pre-computes the transitive closure of the parent pointers.
Which means it mathematically maps out all the topological relationships of the tree at the exact moment it is generated. The chip doesn't have to calculate the hierarchy on the fly. The map is already completely drawn.
But that map requires memory to store. Storing the transitive closure adds an additional 512 bytes to the footprint of every token.
Bringing the total cache slot size to 635 bytes per key.
635 bytes. Which is still remarkably lean for a full semantic token, but it is a massive structural increase from the base 123 bytes. They are explicitly trading cache space to guarantee hexagon processing speed.
It is a totally necessary and highly calculated trade-off, and what justifies this specific architecture is the theoretical security it provides. The sieve design roots the entire memory management system in the WKL zero refutation property, stemming from Weak-Koenig's lemma.
The development team refers to this in the specs as the engineering asymmetry of the Friedman stack.
Yes.
So Weak-Koenig's lemma essentially states that every infinite tree of zeros and ones has an infinite path. But the inverse application here is what creates that asymmetry.
Right. Explain how they use it.
To prove theoretically that the Friedman sieve perfectly filters information requires incredibly advanced complex mathematics. But if the sieve fails, if it incorrectly drops a token it was supposed to keep, or if it hallucinates a match, that failure is guaranteed by the lemma to be witnessed by a finite cheaply locatable mathematical object.
Which is an absolute godsend for the engineers. Think about it. If you are debugging a standard floating point model that is drifting into hallucination, you are literally hunting a ghost in the machine.
Oh, yeah.
You have billions of microscopic decimal errors bleeding together across 90 layers, and it is nearly impossible to find the exact matrix multiplication where the logic initially broke.
But in the Friedman stack,
A bug produces a specific, discrete counterexample. The system essentially outputs an error ticket saying, hey, tree A was supposed to embed into tree B, and the topology failed at node 14.
it's like finding a single mismatched Lego brick instead of staring at a collapsed sandcastle wondering which specific grain of sand gave way.
That's exactly it. And finding that topological counterexample takes fewer than 10,000 operations. It transforms every single memory eviction into a primitive recursive unit test that is continuously running in the background of the engine.
Okay, so the sieve is continuously evaluating incoming tokens, it's dropping the redundant trees, and maintaining the cache. But as this happens, the active cache requires a mechanism to continuously organize and compact itself over time.
Right. It cannot simply accumulate a massive list of partially related floating trees.
No. And this compaction is driven by something they call the choice operator, denoted in the specs as F.
The choice operator enforces a strict total order on all the candidate trees sitting in the active cache. It gives the system a highly deterministic way to pick a winner.
And when comparing memories, it uses a lexicographic packed comparison.
Yes.
It literally scans the 60-byte binary representation of the trees, byte by byte from left to right, and the very first differing byte it encounters instantly breaks the tie.
And remember, because the Friedman sieve has already mathematically rejected any exact homeomorphic embedding duplicates, no two identical trees can ever exist in the active cache at the same time.
All right.
Therefore, the lexicographic scan will always find a differing byte. The choice operator will never encounter an unresolved tie. The selection is absolute and totally deterministic.
But how does that actually result in memory savings? Like, how does a deterministic tiebreaker physically compact the cache?
So when a query token arrives, the attention mechanism doesn't just look for one single exact match. It identifies an entire class of cache trees that broadly match the structural query.
Okay.
The choice operator scans that entire class of related memories, selects the canonical minimum tree based on its byte-by-byte scan, and replaces all the other entries in that class with a pointer to that single winning representative.
Ah. So if the model is holding 4 slightly different mathematical representations of the concept, a large red dog, the operator identifies the mathematically simplest version,
Yes.
deletes the other 3 from the cache, and just points to the simplest one. The cache physically shrinks.
Exactly. The choice operator continuously drives the memory footprint toward minimal witnesses. It ensures the system only expends power retaining the absolute most efficient topological representation of a given context.
That is incredibly efficient. However, I have to push back here.
Sure.
There's an inherent risk in pure mathematical subsumption when you are dealing with human language, right? Natural language is heavily reliant on soft nuance. We paraphrase, we use synonyms, we circle around concepts.
Language is messy.
Very messy. So if the sieve and the choice operators strictly demand absolute mathematical embedding, won't the AI's output become incredibly rigid? Doesn't it lose conversational fluency?
It's a great point, and the engineers knew that. To solve for the fuzziness of human language, they introduced a variable called the Hamming radius, denoted as R.
The Hamming radius.
Yes. It defines a neighborhood of allowable structural similarity. So if you set R to 0, the engine enforces strict, brutal mathematical consistency. Nothing embeds unless it is a perfect subtree. But if you increase the radius R, the choice operator is suddenly permitted to evaluate fuzzy classes. It allows the operator to look at trees that are structurally adjacent, even if they aren't perfect homeomorphic matches.
Oh, that's smart.
By leveraging this Hamming neighborhood, the system selects a canonical tree subject to a soft constraint. This is a brilliant engineering workaround because it mimics standard soft top 1 attention behavior.
So it maintains the fluid conversational nature of the AI.
Exactly. But it achieves it entirely through discrete topological comparisons, completely avoiding the computational nightmare of calculating a massive floating point softmax probability distribution.
Wow. Okay, so we have the entire theoretical foundation now. We have the algebraic stability of heat near -163. We have the zero drift Sato-Tate quantization,
We have the deterministic KSTE encoder.
the hexagon optimized sieve, the 635-byte cache slots, and the choice operator compaction. we have the complete Friedman stack.
You do.
But an elegant white paper doesn't just automatically get merged into a production engine.
No, definitely not.
The Shannon Prime team established incredibly strict validation criteria to actually graduate this architecture into a default shipping feature. They structured it as a rigorous three-tier gauntlet.
And the validation milestones perfectly reflect the engineering asymmetry we discussed earlier. The testing demands absolute primitive, recursive mathematical perfection at the base level before the team even looks at how the model actually handles language tasks.
Right. So Tier 1 is encoder sanity testing.
Yes.
Tier 1 lays out 5 specific pass criteria for the KSTE encoder. And if the encoder fails even one of these 5, the entire production release is halted.
No exceptions.
Test T1.1 requires proof of total determinism. They feed the encoder the exact same continuous key vector 1,000 times, and it must generate the exact bit-identical 60-node tree 1,000 times. Not a single node or label can fluctuate.
T1.1 ensures that absolutely no floating point jitter from the physical hardware environment is bleeding into the discrete encoding process.
It has to be sealed.
Completely sealed. Then, test T1.2 validates the order invariance we covered earlier. They apply the Frobenius shimming scale factor, essentially multiplying the input vector by a massive constant proc, and verify that the resulting tree topology remains completely unchanged.
Proving that rescaling doesn't break the map.
Exactly.
T1.3 tests sign-respecting logic. If they input an inverted negative version of a vector, the structural depth of the tree must remain identical, but the encoder must perfectly swap the B and C labels across the nodes.
Yes, and T1.4 and T1.5 are strict budget enforcements. The process must never exceed the 60-node maximum limit, and the top 14 magnitude selection for the anchors must perfectly match the children attached to the root node.
So, assuming the encoder achieves mathematical perfection and passes all 5 tests in Tier 1.
It moves to Tier 2, sieve behavior.
Right, and this tier represents the actual gating test for production deployment. They're evaluating whether the sieve's topological filtering actually damages the model's intelligence.
Test T2.3 is the ultimate gatekeeper here.
T2.3 mandates a perplexity or PPL ablation test on a Gemma 3.1b model.
Right. And perplexity measures how confused an AI model is when trying to predict the next word in a sequence. Lower is always better.
The validation criteria demands that the perplexity drift with the Friedman sieve turned on versus the standard memory architecture must be less than or equal to 0.5%.
It is an incredibly tight margin.
Insanely tight.
Think about what they are doing. They are radically altering the fundamental mathematics of the model's memory, completely stripping away continuous variance and demanding that the model performs almost exactly as well as it did before.
If the perplexity degrades by 0.6%, the entire architecture is scrapped as a default feature, regardless of how theoretically beautiful the math is.
Yeah, engineering doesn't care about beautiful math if the product gets dumber.
And they also pair T2.3 with a strict efficiency requirement. Tier 2 mandates that the sieve achieves an eviction rate of at least 20%.
Right. The sieve has to be actively throwing away at least 1 out of every 5 tokens it processes.
This proves that the architecture is genuinely reducing the memory footprint and not just hoarding every single tree it generates out of a failure to find valid embeddings.
So if the Friedman stack passes the perplexity ablation and the eviction threshold of Tier 2, it ships. It literally becomes the default memory architecture for the engine.
But the documentation doesn't stop there. It outlines a Tier 3, labeled as an ultra-product attention experiment.
Now, to be clear, this is not a shipping requirement for the current release. It is a long-term research objective.
Right. Tier 3 tests whether these topological tree structures can be scaled up to entirely replace standard softmax attention mechanisms over massive documents.
Yes.
The success criteria for Tier 3 is matching or beating standard softmax attention performance at a staggering 32,000 token context length, while keeping the processing wall time within 20% of the baseline.
Which is huge, because if they crack Tier 3, they aren't just compressing cache memory for local mobile devices, they are entirely rewriting how foundation models process entire books of information.
The scope of what the Shannon Prime team has engineered here is honestly remarkable.
It really is.
They identified the foundational flaw in AI architecture, the non-associative drift of continuous floating point mathematics, and they literally rebuilt the system from the algebraic bedrock up.
We have walked through the utilization of Heegner -163 to establish a unique factorization domain. We explored how the Haswell bounds perfectly define the true Shannon limits of the transformer's capacity.
We looked at how Sato-Tate mixed precision leverages inert primes to achieve zero-drift quantization without needing a single byte of calibration data.
We examined the KSTE translating messy 128-dimensional continuous vectors into crisp 60-node topological trees.
And the hexagon-optimized sieve running those 300-600-step embedding checks to ruthlessly drop redundant data.
Right. And we evaluated the specific memory trade-offs, like the 635-byte cache slot, utilizing transitive closures to guarantee speed.
All culminating in the rigorous multi-tiered validation gauntlet required to actually take this from theoretical mathematics to a shipped, production-ready engine feature.
It is a phenomenal intersection of abstract algebra and edge device hardware engineering.
It really is. But, stepping back from the hexagon chips and the perplexity ablation test for a second, the core philosophy of the Friedman stack leaves a lingering, really provocative question.
Oh.
Yeah. If the cutting edge of artificial intelligence memory is fundamentally shifting away from storing continuous, blurry values and moving toward caching discrete topological concepts that automatically subsume one another,
Yeah.
what does that imply about the nature of knowledge itself?
That's a deep question.
I mean, could it be that the human brain relies on a remarkably similar sieve? We naturally toss out redundant, fuzzy daily experiences, right? We blur the minute details and we retain only the purely novel, distinct trees of memory.
It makes a lot of sense from an efficiency standpoint.
Exactly. So by forcing AI to abandon continuous math and adopt this rigid topological filtration, are we finally just teaching silicon to remember the way organic minds have done all along? Something for you to mull over.